Yo, 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 what's up, everybody? Welcome back. Today we're working on training neural networks from scratch. Day one, new project, baby. Okay, so context is I was making a food tracking app, and as part of the food tracking app, what do we need to do? We obviously need to track all of the stuff in our fridge so that we can, make grocery lists and, I don't know, make it easier to write down how much of stuff we use. I don't know, it seemed like a good idea. How do we track stuff in our fridge? We scan it with the barcode scanner. I don't have a barcode scanner, but I do have a cell phone. So, in our food tracking app, we could make a page on the website that you take out the camera on your phone, you point it at the thing, it goes beep, and it goes, hey, you added milk to the fridge, huzzah. So we started writing a barcode scanner by hand. We got decently far, right? We made it overcomplicated for ourselves. Specifically, there were cases where there's warping in the barcode, and edges can be ambiguous. Sometimes the barcode is kind of slightly occluded, blurry, whatever. So we were going down this route of trying to do some sort of intelligent clustering of edges, whatever. We tried a bunch of things. Basically, it was just taking longer than I really wanted it to, and I think that eventually I can only slam my head into the wall so many times before it becomes boring to watch, right? So, what do we do when a problem is too fucking hard? We give up. We give up and we say, computer, please, can you do the problem for me? Right? You might say, why didn't you just do something simpler or look up the answer? Shut up. That's not the point. Okay? Okay, we want the computer to do it for us now. And so that brings us to neural networks, right? This is a problem that's pretty good for it, right? In ambiguity, what am I doing when I'm looking at this thing? Well, I'm looking at the barcode color next to adjacent colors. I'm kind of using local contrast, not global contrast. I'm kind of inferring where lines would be when things are blurry and making guesses with a bunch of hand wavy info that I don't really, it's hard to articulate, right? It's the type of thing that I feel like a neural network would be pretty good for. And so, obviously, if we're gonna make a neural network, we have to build the whole thing from scratch, or else we're cheating. It's illegal. We're, breaking the rules around here. So, that brings us to today. Today, I think I want to start with training, the world's simplest neural network. If we can get to the point where I can say, hey, given two numbers, which one is bigger? Which one, this one or this one? That would be pretty good. I think that's a really good starting point. If we get to that today, I think I'll be pretty happy. So, let's say we gotta dump our context. How do we think neural networks work? I will say that in typical fashion, I did not very much research for this, and we're going off vibes. But over the course of the past 5 years or whatever, I've worked with them a little bit. I've watched some videos, and so we can probably piece together something pretty reasonable. I would say if you're looking for resources, there's a really good video by Sebastian Log, I think is his name, Lague, something like this. He has a banger first episode on neural networks, start to finish, and then also 3 Blue 1 Brown also has a pretty sick 8-episode series on this stuff that I think is pretty good if you're what the fuck do these things do? But for now, I will just kind of go off what's in my brain, and if it's wrong, it's wrong, and you guys can sue me, and well, don't sue me, please, but you guys can yell at me, so let's start with our simple problem. Our problem might be a little bit too simple to go into all the details, but we can kind of start there. I have 2 numbers. We draw them as circles because everyone else draws them as circles. And if we want to say, hey, which one of these is bigger, we draw lines like this. Now, we're going to gloss over details of we're going to gloss over the fact that this can be solved in a simpler way, right? Because we're just trying to start with a simple example. But we'll say that as we go from one number to another, we're going to do some multiply adds, right? So we're going to take number 1, or we'll call this number A and B, and we're going to multiply A times some number, weight 1, and we're going to add it to B times some number, weight 2, right? That's that's kind of like the core of neural network training. Now, later on, we're going to like stack a bunch of these together. So like a typical thing you'll see is like some diagram where they kind of like draw like a bunch of interconnected lines into like a bunch of interconnected nodes, kind of like this, and then like, you know, these guys are used together to like form some sort of output, right? Bloop, 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 right? But like we're starting simple. So each line and each node is kind of like being like, I am multiplying and adding a bunch of stuff together. Now, this could get you some reasonably good behavior, but you know, this centers around 0 all the time. You might want to like offset stuff, so you throw a couple biases on there. You add like, you know, plus bias 1 and bias 2 is kind of like, you know, for each of these guys you offset the line, right? You can imagine that if you had like a bunch of points somewhere in like some graph and you wanted to like bisect these, you could like bisect them with a line that goes like this, right? And you could say like everything on this side of the line is like one thing and everything on this side of the line is another thing. But to do that, you need to be able to like offset the line, right? So it's like mx plus b, right? For like line formula, right? And then you just kind of like say, now like do this a billion times, right? Do this a bunch of fucking times in a row, and you can like build maybe like some complex behavior, right? So if you wanted to like make something that was like curved through this space, you could kind of like approximate a curved surface through like a bunch of smaller lines, right? So you can kind of go like boop, 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 boop. Let's say I wanted to do like this or something. Well, you could kind of like do one line that looks like this and one line that looks like this. And as like the dimensions of your data go up and like the split between different things becomes harder, then like you need more and more lines. Like maybe also like the stuff up here you want to be in the sum set, right? Now you need like 4 lines or something like this. And like you need some way to say that like I want to turn the lines on and off. And so like what they'll usually do is when they have like multiple layers of stuff, they'll kind of just be like, okay, instead of like just being any number in here, let's just say it's easier to think about zeros and ones. Hand wavy, so they might like huck that shit through some function that looks kind of like this, right? So you go like whoa, or maybe like this, so that like every number is between like probably more like this. Every number is between 0 and 1, right? Just so that you can kind of like allow like the multipliers to go like as high as you fucking want. You can take any number as an input, but then later on you're just like ones and zeros, baby. This allows you to do, if you have everything as like 1 or 0, that allows you to do some, like, you can imagine that if you wanted to say, I want to know if like, you know, attribute 1 and attribute 2, are these both true? If these are both numbers between 0 and 1, you can just multiply them together, right? So it allows you to like build up like complex behavior by saying like, is this thing true and this thing true? I can do that by multiplying, which is just like another fucking thing in my graph of multipliers, right? Or if you wanted to do or, you could do 1 plus 2, or sorry, we should be using letters here, x and y, right? You could do x plus y to be like, are either of these things true, right? So if you're like trying to do something like, in the 3 blue 1 brown video, they use examples of like a digit. You might say like a 9 is different from an 8, right? But like both a 9 and an 8 might have an attribute that say there's a circle at the top, and so 9 might be like circle at the top plus like and line on the side, and 8 would be like circle on the top and circle on the bottom. And you can build up to this by multiplying zeros and ones together. So that's kind of like my understanding of what is supposed to be going on here. The reason that you're going to use like some sort of like smooth function like this to turn things into zeros and ones instead of some like, you know, just complex, like just boom, 0 or 1, is because in order to figure out what these numbers are, what these weights are, you have to be able to nudge things in the right direction, right? So instead of us being like, I know the answer, right? Back to our like original idea. Our original idea, if we're trying to say, give me a neural network that says, is A greater than B? 1 if true, 0 if false. You could probably, like, if I were to make this up, I would say, like, you would make weight 1 here, 1, and weight 2, -1, right? And then this thing would be greater than 0 if A is bigger than B, and less than 0 if B is bigger than A. And then you slap that through that little squiggle curve, and that becomes like something towards 0 and 1. In reality, you want these things to get like really pushed far away, so you'd probably get like weight 1 really fucking big number, weight 2 really fucking big negative number that are like approximately equal. But you don't know that. Like we can make those weights up right now because we have like a really simple problem. But say we don't have like a simple problem. We don't know like the real answer. But we do have like examples. We don't know how to get the right answer, but we have examples of the right answer, right? What we can do is we can define like some function of how fucking wrong am I, right? So we like just huck random numbers in here. We say like negative 1,005, right? We say, okay, let's throw some numbers in here. We put in 10 into A, and we put like 8 into B, right? This would become like negative 10,000 plus 40, right? 8 times 5 and negative 1,000 times 10. And we'd be like, wait a second, that doesn't give me, and then you put this through like the sigmoid, this like little s function, and this would become something like relatively close to 0. And we go, wait a second, we don't want this to be 0, we want this to be 1. And we'll be like, okay, hand wavy, we'll skip over the math for now. What do I have to do to these two parameters to push them towards the right answer? So we could come up with some number that is like, how fucking wrong am I? How wrong am I? And in this scenario, the answer is a lot. We're very wrong, right? And we could, if we have a number that's like really big, if we're really wrong, and really small if we're like almost right, you could say, how do I make that number 0? Right? What can I do to like make that number smaller? And we're gonna like do just a teeny weeny little calculus, right? A teeny little bit. We don't have to think about it that hard. We can Google all of the hard parts. But hand wavy, if you had some function where, let's say you have like a single parameter, right? And you're trying to make, this is like the incorrectness function. They call it loss, right? So like big, bad, small, good, right? And let's say that like, let's just say we were trying to say, we want to know if x is 0 or something. Like, the farther away you get from x, the more wrong the number gets, right? And if you look at like this line, you're just like, oh, okay, if I'm here, I need to go that way, right? Like, because let's say that the function's actually more complex. We don't actually know what the function is, and maybe it's like not really like a simple function, right? Maybe the function looks like something like this, right? Just like for some values of x, it's like kind of right. For some values of x, it's kind of wrong. Or maybe it's easier to think about it like this way, is probably the first thing to draw. So like, if we're like over here, we're like, I guess if we were to look at like the slope of this line right now, we know that like we should go that way, because that's down. We like going down towards 0. And if we're over here, we're like, oh, let's go that way. And this is called like gradient descent, where you're just like, hey, let me like look at like how much I'm changing. I don't really know what function I'm a part of, right? This works for any function, for like a line, a little like parabola, or something that like looks like this. You can kind of do this concept anywhere where you're like, oh, I'm here, I'm gonna walk down to this little hole here. Or like, I'm here, I'm gonna walk down to this little hole here, right? Or like here, I'm gonna keep going to this way. So like, if we can define our some function that's like, how fucking wrong am I? And we can take the derivative of that function to find out which direction makes that number smaller, we can just kind of like go that way. And if you have like a complex function, you know, that like has like a bunch of like local minimums, like say you're like over here, you don't want to get stuck here, you can kind of just like overshoot. You can just go like really far this way, and then you'll like probably like eventually, if you start like jumping back and forth enough, eventually you'll probably end up like somewhere pretty decent, right? Because you can probably assume that the like actual function looks like a little bit more like, you know, like this, right? There's like kind of like some sort of like wiggliness to it, but like overall it's probably trending towards some sort of like nice little area in the middle, right? So that's kind of hand wavy what we're trying to do. So how do we come up with that? Well, let's kind of make some new space. So we have, what do we talk about? We have like 3 things. There's like loss, right? How wrong am I? There's the like this squiggly function. They call it activation. Activation. And then there's like the like multiply adds, right? Mul plus add. And it turns out hand wavy relu, yeah, you can have like many options here. There's like sigmoid is what I was looking at, was talking about, but there's like relu, there's a bunch of other ones. Basically something that like turns things on and off but also is differentiable. Then there's like the multiply add part, which is like, you know, the weights and the biases times like the numbers that we start with. So if we want to know how like if we want to know how like number weight 1 contributes to the total loss, there's this like thing in calculus called chain rule. We don't have to think about it as a rule. We can say, hey, there's like a bunch of steps happening here, right? Imagine that you have like x squared, right? Derivative of this, you take like first year calculus or like grade 12 calculus, whatever. The rule is like, for some fucking reason, if you want to know the slope of x squared at any point, you just like take the power and move it down here, right? So the x squared, the slope of this function at any point in x is 2x, right? Now, let's say that x, though, we got x by doing a bunch of other shit, right? So maybe we have like some parameter y, we say y multiplied by 5, 5y, and then we square this thing, right? Well, we know that the slope of this thing is 2x, and the slope of this thing is like kind of 5 times whatever the slope, right? Any change in y is going to have like 5 times the effect in this scenario, right? And so it turns out that the derivative of this guy is 5. And so if you just like multiply the derivatives together as you like stack operations, that can tell you how much like that thing contributes to the thing at the end, right? So while, you know, change in x results in like 2 times the slope, the slope at some point here is hold on. Slope at this point is essentially like how much do we change if we walk in forwards, let's say, right? So in this guy, it's like we walk 2x. Yes, we're gonna move 2 times x in some distance, but then like that number is multiplied by 5 because we were having 5 times the effect. Hand wavy. So what we need to do is we need to figure out the derivative of each of these guys and just kind of like chain them backwards, right? So back to our little example of you have 2 numbers, you're adding these together to some output. This is turning into, you know, weight 1, weight 2, times like parameter plus bias 1 plus bias 2 times parameter 2, right? So these guys are all both going through like activation function, and that's going through, is that it? Then we're calculating loss. Yeah, something like this, loss. Yeah. So you can just like chain these derivatives backwards. And so what we need to do is like keep some sort of graph, I think, of like how each parameter is getting like, you know, if we want to know, we want to change weight 1 here to kind of like bump this thing down, this loss function downwards, we kind of have to like keep the chain of events that happened. That's my current understanding. I don't fucking know. Let's just fucking run it and figure it out from there. Okay? Let's figure it out from there. So, the plan of action is we're gonna like build the graph going forwards as we forgot to add the P2 into the loss. Yeah. Yeah, true. The loss is like sum of like all of these guys, right? Act, you know, parameter K times weight K plus bias K or whatever, right? From like K equals 0 to like param num or whatever. Right? Something like that. Whatever. I'm looking at this, I'm a little unsure about derivative of the loss function. I might have to look that up when we go a little forwards. I'm not 100% sure. My mental model, I'm not 100% here. Because like I don't know if the loss function has to be differentiable. I guess it probably does. I guess it does. We'll get there. We'll get there. We'll figure it out. But first, we need to figure out what set of operations results in something happening. And so, I think the plan is, I don't know, build up a graph somehow. Now, later it will be easier to think about these things in terms of batches of numbers, because that's what, like, when we eventually get this stuff onto the GPU, we're gonna have to do it that way. But for now, I think it'll be easier to do it this way, to just like do, you know, one number at a time, because I can only think about one number at a time because my brain's super serial, unlike GPUs, which are super parallel. Okay, here's our library name, Smelly, because it kind of like sounds like ML, and then we throw a SPH in front of there, and I think it's funny for us to be smelly, you know? So let's do that. Fruity Pebbles ass, yeah. Stupid cereal brain. So only Cheerios and Fruit Loops up there. Okay. I don't know. Let's do something. Let's make a main. Every program starts at main. And we write an error out here so that we get like some free standard out, zig, run, source, main. Hell yeah, dude. Uh-oh. Okay, so we want to build something that looks... Where's our little picture? Hello? Our picture was 2 parameters, 1 output. We need to make this. So, we have... Yeah, I guess we have, you know... weights? Sure, we have weights that I guess in this scenario is like 2 floating point numbers, and we'll initialize these with random numbers later. We have biases, which I think actually probably aren't needed for this problem, to be honest. But, you know, this is the typical neural network thing, so we'll do that. Yo, that's my brain is a very funny message. And then what are we doing with these things? We are, I don't know, we're like doing, I guess we have 2 numbers. So I guess we'll take these from standard input. No. We'll have to take these from somewhere. So maybe we like define a network. That feels a little bit more reasonable with some weights and some biases. Okay. Okay, and then we can like use this network for training somewhere and then for like execution later, right? So if we are in, I don't know, let's say that we look at the standard input. I guess we make the network here. Let's start there. Easy. And we probably need to like initialize these with some random weights. Yeah, let's do that. Here we go, we're getting somewhere. I think I'm just gonna delete this link because I don't want to look at it, and I don't really trust that it is, I don't really trust it. But not be, you know, not to say that you can't post links, just that I don't really want to look at it right now. You know? I think that these guys are going to be initialized with, well, let's figure out initialization later. We can just ignore that. Yeah, let's do that. Let's just do that. We ignore it. When we run this network, we're gonna run it with 2 input parameters, right? 3 and 10. Yeah. Yeah. And this guy is gonna have some sort of output, which, according to our very complicated graph, is 1 floating point number. Okay. Here we go, we're getting somewhere. And what is he gonna do? He's gonna say, let's run this by multiplying these guys together. So we say self, I guess it's self here, with, you know, A and B. We're gonna be like, weights 0 times A plus Biases. 0. Yeah. Yeah. Hold on, we're getting somewhere. We take these guys, and then we add in, the second weight and bias. So slap one of these on here. Okay. Yep. And then all of these guys go through the, this function, which is called sigmoid. Okay. Here we go. What's sigmoid? Let's look it up. I don't fucking know, man. Sigmoid. 1 over, here we go. E to the x over 1 plus e to the x equals 1 minus sigmoid negative x. Okay, sure. So we just pick one of these. 1 over 1 plus e to the negative x. Okay. I'm sure this will become more complicated later. Slap on a ReLU. Yeah, I mean, I think that it's easier to think about with sigmoids, but I do think that later we will change to ReLUs. I have to do some reading on why. My understanding at this point in time is that ReLU is a cheaper activation function that's less obvious, but it doesn't really matter. It it ends up with training faster with maybe some more parameters, but maybe faster training. I don't really know. Okay, so this guy takes in F32. And he returns an F32. Okay. And then we're return 1 over 1 plus we probably need the same library here. Stud math exp, right? This is base e exponential to a floating point number to negative n. Easy. Easy, easy, easy. It's simple. Simple, simple, simple. So this is what we're trying to make. Now, can we say const output is this, and then can we run this thing? Or print it. Okay. That's looking like you're getting somewhere. Now, why is he mad? Because we didn't use B here. We used A, like a dumbass. Easy. Okay. So now we have to initialize these things. So let's just initialize them with, I don't know, zeros for now. Random numbers would be better, but I don't want to pipe a PRNG around there. Since you've done some graphics, the structure of the multiplication has the same commonalities as homogeneous coordinates. It's basically mat weights biases times vectors 1. Yeah. Do you need the homogeneous in there? I thought that you could get away with I think that it's just weights times biases. I think, but I could be wrong. I think you just put all the weights in a box, and then each layer of the network is a matrix multiplication with the last layer. I think, but I could be. Not sure. Not sure. I have to look into it a little more. Okay, let's for now say weights is equal to 0, 0, and biases is equal to 0, 0. Easy. Easy peasy. And so, what are we expecting to get here? It said 0.5, which is actually surprising. I would have expected 0. Oh, because we're running it through sigmoid, right? So we get 0 as the output, we shove that into the sigmoid, and the sigmoid is 0.5 at 0, so that this is reasonable. This is we're running through the stuff. Now, this is not very useful, right? Because if we want to do backpropagation here, what the fuck are we gonna do? We don't know what's going on, right? We would just have floating point numbers. Ew, gross. So I think what we need is some sort of I don't know, some sort of number where we can track the graph of what happened to him, right? So when we do backpropagation, eventually we're going to be we're gonna get to the end and we're gonna be loss. What was my loss? And we can be we need to be how did we get here, right? And we're gonna go backwards. So backwards we're gonna have some sort of I guess the loss is gonna be, in this scenario, we're kind of lucky that our loss is just how far off were we from the right answer. So we're going to be was the correct answer 1 or 0? And we can probably just do what did we get? X, and subtract it from this, and then absolute value it. But, you know, maybe that's like not as nice as squaring it, because mean squared error is a thing that you'll see later, where we do like add up all of the things that we got wrong, square them all, so that like it has some nice properties. One is that squared is always positive. Two is that it like amplifies big errors more, so that they kind of like contribute more, and so we like focus more on things that are really wrong than things that aren't really wrong. So let's do this. This is also like, I know how to differentiate this, where differentiating abs, I guess I know how to do that too, but this one's really simple. You just bring the 2 down, right? So let's do this. Let's do this. So we're going to need to say that like we calculated the loss, right? And that was like made up of some inputs, and we need to like find the derivative of that. And then that went through like sigmoid, and then that went through some like multiply or add, and we're gonna have to like figure out like how we got here. So I think I want some sort of like just like linked list of nodes. Seems kind of reasonable. I know this isn't how you would do it later, but we're trying to think of some structure where when we're calculating derivatives, we only have to calculate each one once. So having some sort of like way to track that seems nice. And then like later as well, if we had like 2 things that we were trying to like track here, can I just like bring this down? Right, like you're gonna have like many computations branching off like the same point, right? With like other inputs from here and here, right? And so like understanding that like we only need to calculate the derivative of this guy once. I feel like this is very like node graphy, you know? That's just kind of how I'm feeling. So let's say that we have some tracked floating point number. Okay, and he has a pointer to like where he came from. Right, so let's see, what do we support right now? We have sigmoid, we have multiply, which this takes like a times b. We have add, this takes a times b, right? This takes in single parameter, and then our loss function is like a sum of a bunch of things. So you can say if we're summing, you know, a plus b plus c plus d, right? You can compose this of like many sums, right? This can be like sum of this, then sum of this, right? And then sum of this. So everything can be represented as 2 numbers, I think. So let's say that we have in 1 is a pointer to another tracked floating point 32. In 2 is a pointer, like optional pointer, because it might not exist. I guess both of these might be optional, right? Because like maybe you just have like a constant, but maybe your constants, yeah, they might be, we might need them, so not sure. And then we have value, which is an F32. This might be fucking stupid, but you know, whatever. Well, later this will get like optimized into something much better, but this is like the way that the problem makes sense in my brain right now. And then we need some sort of like operation that we apply to this thing, right? So operation, I guess. And for now, I think that, you know, just having an enum of all operations that we could do seems reasonable. Maybe it's not, but maybe it is. And like right now, what are we gonna do? We have like add, we have mul, we have sigmoid. Right? And then like square, like pow as well, I think, to do loss. Something like that. Right? And so now all we need to do is like say, how do I make this thing, right? So init from, you know, val is an F32, it gives me one of these guys, and I guess we have init as one operation here as well. I think that's reasonable. So this guy's like, I have val is val, up equals init. We have in1 is null and in2 is null in this scenario because there are no inputs to initialization. This value just came from fucking nowhere. We have add, so we take in self as a tracked F32, pointer, not pointer, pointer. And we have a, which is also tracked F32, and b, which is a, I think it's actually a and b, no self. Yes. So this will return a new tracked F32. maybe as a pointer, I think using pointers everywhere is going to make this easier. So, because like we can then just like slap them on some allocator, reset the allocator every once in a while, whatever. But like that way, I think it makes sense that way. Because these things need to have stable memory locations so that we can like do the backpropagation. So I think this makes sense. Let's do it this way. Let's do it this way. And so here we're going to be like, what? We have val is a val plus b val. Easy. Easy, easy, easy. No way we're doing N's and C. It's actually in Zig, but very close. Very close. Basically the same shit. So I think it's just like this, right? In 1 is A, in 2 is B. And then we can kind of just walk backwards from there. Simple. And we need to return these guys we need to allocate, right? So unfortunately that means that everything is gonna have tries everywhere, but like fuck it, I guess, whatever. And I guess we do like ret is try stood alloc create. You know, one of these guys. Sure. Ret.star is equal to this, and then return ret. Okay. This seems reasonable so far. So far. Oops, sure. And okay, now we just start slapping in different guys, right? So multiply is A times B. Okay. And sigmoid. Sigmoid is only single parameter in, so in2 is null. We forgot to change this guy to say that he was a multiplication. And this is sigmoid of this guy. Okay. Easy peasy. Yeah, sorry, by the way, I apologize for you guys if you are saying stuff in chat and I'm ignoring it. It's because I'm too stupid to work on this and answer and read chat at the same time. So I apologize. I understand that that's maybe not great. This is ambiguous, huh? So can we do, how do I disambiguate this? What if we just don't? The easy fix is to do this. Easy. Actually, maybe we should leave this function here, though. Oh, I guess we can actually do tracked f32 dot, or no, fuck. That's the one we don't want. Yeah, I'm just gonna copy paste it because I don't want to think about namespacing right now. This is not important. Not important. Okay. Okay. Do I understand correctly they're gonna use deep learning to recognize barcodes? That's so neat. That's where we're gonna end up, yeah. Why did you use Zig? Just because it's like the language I work in right now. It's the one I find most satisfying. It has like a bunch of like attributes that just line up with my current value system. Okay, last one is power. Power. So we have pow, A and B. And this is gonna be stood math pow a b. We're saying that this is pow a and b are our two inputs, and now this should be everything that we need to like walk backwards. Re-graphics, the relations that you can package all parameters of a node, weights and biases in a single matrix, just like you can package general graphics transformations in a single matrix. Yeah, agreed. In both cases, you need a pad input with a homogeneous one for stuff to work out. Okay, that's not my understanding. Oh, I see. I understand now. You're saying that you can put weight 1, bias 1, weight 2, bias 2 in the same matrix. And so for you to use this guy, your inputs are, you need to throw the 1 into the bottom to make the bias work out. I was thinking of it as like weights plus biases in its own vector. You know what I mean? Like in its own matrix. But I understand what you're talking about now. I understand. Okay. So this guy works with tracked F32s now everywhere, right? And we are going to be like, each of these is now like this. But this needs to come from some allocator. Sure. And um is that true? I think so. Fuck it. You know, fuck it. That's what I always say. Okay. Cool. And so now here, instead of doing this stuff, we are running the network here. So we have like a tract, I guess, is, we need an allocator here as well, is tract F32 and an A, B tract is B, okay. Then we can do self weights 0, mul, A tract, okay. Then we add to that number self biases 0. Okay. A out or something. For B, we do 1, B, 1. Okay. And then we return A. We return the sigmoid. So tract F32 sigmoid of A out add B out. Okay. Yeah. So far, looking kind of good. So far that looks reasonable. Now, if this guy is still doing all the right math, we should be able to see the same 0.5 here at the end. We do need an allocator, so var mem heap arena allocator initialized backed by the page allocator. Eventually, we'll probably pull in our allocator system, but for now, this will do. I think. And let's just see if this compiles and runs. No, because everyone here needs to be tried. Everyone needs to be tried. Okay, so blah blah blah, expected this. This guy is failable, true. Because allocations can fail. And these guys are returning pointers now. These guys are all pointer returns, so we're chilling. 89 is mad because these guys need to be pointers here. Okay. Sure. Run needs an allocator. Okay. And no field name mul in track 3 F32. Okay, so why not? Because I took in the allocator as the first guy like a dumbass. Okay. This kind of blows having to like pass this allocator everywhere, but it's fine. Okay, we'll work with it for now. Tract F32 mul alloc weights a tract. Okay. Yeah, this sucks for composition. This really sucks. Can we? So it will be useful in the future to be able to like nuke sections of the graph at a time, right? Like the weights for the network, we kind of want them to live in a different lifetime than all of the downstream stuff that comes from them, I think. But for now, we'll just do it like this. It's fine. We'll find because this is going to change in the future anyways, so it's fine. Tract F32 add alloc this thing like this. Okay. Yeah, we can make that work for now. And then, why is he mad? Okay. Yep. And then B out looks similar, but with some ones kicking around here. Uh-huh. And then this needs alloc A out, B out. All right. A out. Nope. This is A out, add B out. There we go. Okay. Are we close? Fine. Okay, so we still get 0.5 here, which is a good indicator that we haven't really fucked this up. And it might be nice to, like, look to see if we have, like, the correct chain of actions, right? So can we say, like, who did this guy come from? Yeah. So can we say, like, uh, like print net or something. I don't know, man. Or yeah. Yeah, sure. Print the network of stuff that happened. So we're gonna have some like input as a tracked F32, and we're gonna return nothing. We're just gonna print stuff. And I think we're gonna have like an indent level here, certainly, because this is gonna be like some sort of tree walk, probably. And we're gonna be like, I guess we print the input, this thing, right? So it's like probably some name with some value, I guess, is what makes sense here, right? So like, we're gonna start with, tag name of input op. So this was like some operation that came from these guys. So he's, oh, this is his value. Yeah. And then I guess we're gonna say like if, input, in 1, we print the network again, but with the indent level up by 1. And this we print in 1. And then we go into. Okay, yeah, okay, that's reasonable so far. And then here, I guess we have to say like for 0 to indent level, we print some tabs, I guess. I don't know, man. Print net output. Close. Okay. So this sigmoid came from an add. This sigmoid came from an add who had 2 parameters, which came from a multiplication with 0 and some 2 parameters. Oh no, sorry. This add came from this multiply and this initializer. So this is the bias 1. This is weight 1. This is this is our parameter input. This is weight 2, parameter input, bias 2. I think this is right. I think we have a graph of how we got to this answer. And so now we just need to throw on the last piece here. So we can say loss is going to be like our expected answer. Okay. So we're expecting 3 to be less than 10, so this should be 0. Right? And we're gonna say this is expected. Okay. Loss is going to be something. Something. Let me think. My poor stupid little brain. Expected sub. We need sub. Which I think is kind of just an add if you think about it. I think. I guess it's like multiply by -1 and sub. And then add. So I guess having sub in here is fine. Having a function for sub will make our lives easier, so we just do this. Sub, minus. Okay. So this is expected. This is gonna get old fast, but whatever. For now. And then we square this. Pow. And then we do init too. Okay. Okay. So does that work a little better? Fuck. Pow is mad. Because stdmath pow requires us to pass in the type that we're powering, which is fine. We'll live. And this needs vowels here and here. Okay, so we have power 0.25, which comes from subtracting 0.5 from 2. That 2 seems wrong, no? Oh, I see, my bad. This is a power of this to 2, right, which we're subtracting the correct answer 0 from the sigmoid of 0.5, and that's coming from an add of these two numbers. Okay, got it. This seems right. I think this is the correct chain of actions. Which means that our forward pass is done. So, backpropagation. What do we need to do here? Remember, we said before that, like, we get there by finding, like, the derivative of each of these guys and multiplying them with the derivative of the guy previous, right? So, what we need to do, I guess, is request the derivative of this guy. Yes. Yeah. So, what does that mean? I don't know. Where's this gonna go? I have no fucking idea right now. I have no fucking idea. But we will see. So, switch on our operation, right? The derivative is going to be different for each one. And I guess we need to think about, okay, so if I do A plus B, how much does a change in A affect the final answer? It's 1, right? It's just 1. Like, if I move A up by 1, that changes the final answer by 1. I think that's right. If I have A plus 2B, how much does a change in B change the final answer? Well, then it's like 2 times B. Yeah, so I think... Okay, so that makes sense. If I'm looking for the derivative of like a single parameter, that's like easy to calculate. Now, if you have like a multiplication of 2 parameters, A, B, we need to like determine which of these 2 parameters we want to be deriving for, right? Like, any change in B will move A in that direction, and any change in A will move B in that direction. So I guess here we need like an index. Or maybe we don't calculate derivative here. Maybe we do backprop. Maybe we just do backprop and tract F32 can like own a like gradient thing here that is by default initialized to null. Okay, yep, that makes sense. And for now, I'm actually just gonna write equals null here. Okay. What keyboard do you use? It's just like a 60% cherry brown keyboard. Okay, so what we'll do here is when we backprop, we're basically going to be doing the same thing as when we print the network, right? We're going to go through each of our parents, check if we've already calculated the gradient because we got there through some other path, which is very possible. And if we haven't, calculate it. Okay, cool. And then we should be able to know how this parameter affects the final output. Is that true? Do we need gradient with respect to each value here? We might. So how does a change in 1 affect my output? And how does a change it to 2 affect my output? That feels more like my mental model of this, right? We have A, B. How does a change in A affect the final output? How does a change in B affect the final output? Like, that depends on how they're used downstream, right? So I think that that makes sense. I don't think that, like, A doesn't have, like, a single gradient value, right? He kind of has, like, a gradient value with respect to how he's used, I think. Maybe I'm wrong. But this is what seems reasonable to me right now. Okay, so when we do backprop, so add is simple. Let's just start with add and then work our way forwards from there. So I guess this thing's a pointer probably, and we have like, all right, I guess init is return. This is our exit case, right? We've hit a number that has no one who he came from. He's just like some base number. I'm thinking. I've changed my mind, I think. I think there is. Okay, so say we have A, B plus AC is the final output, right? A is contributing to the total answer, you know? He's contributing this twice, right? He's moving it by B plus C every time he moves. So I guess when we're walking backwards, we might want to like add to the gradient every time we see it. That's kind of how I'm feeling now. Is that as we go backwards, we have one gradient and his initial value is 0. And as we find him from different places, we add on to him. I like that. That seems maybe reasonable. Maybe. I don't know. Okay. So if we are adding, we say self in 1 gradient plus equals 1 in 2 also plus equals 1. Okay. Mul in 1. So in this scenario, we have A times B, right? So any change in A increases by B and vice versa, right? So the gradient of 1 is added by the value of 2 and vice versa. That seems reasonable to me. Power. I'm gonna change power so that the thing being taken to like A to the power of B, I don't want B to be tracked. That's my new thought here because I don't know how to do that, right? So in this scenario, now figuring out the gradient of A is quite easy, right? Like in 1's gradient is just 2 times the something. Hold on. So if I have like A fuck. So x squared, I know that like the derivative of this is 2x, right? Where x is the value. Okay, so this should be like ooh. Hold on. Fuck. Because we need like the power that came in here. So can we say that into? Oh, we'll just do this for now. we need to write down what the power was. So can we just do like into raw is equal to b for now, and then we can say the gradient here is our value that came in times into raw, right? So we like add 2x to the gradient, I think. Maybe? What's the name of the keyboard? It's just a Durgard K320 or something. I don't know. I don't think that my keyboard really matters. I don't think you should care what my keyboard is. Because I just like fucking Googled 60% keyboard and then picked one. Like, I don't do like, my purchasing is like fucking stupid. Okay, sub. I think that this is the same as add, but one of these is negative, right? So yeah, I think it's like this. I think. I don't know, but that seems kind of reasonable. And then the only thing we're missing is sigmoid. So sigmoid derivative, I'm sure we can just like sigmoid derivative. Blah blah blah. Differentiate is sigmoid x times, oh wait. No, that's not the answer. Wait, maybe it is? Can we just like derivative of sigmoid? Does it just tell me? Yes. Derivative is e to the negative x over e to the negative x plus 1 squared. Alternate forms? Sure. Okay. It's this. So, x is, I guess, yeah, it must be N1 val here. Yes. And then we have e to the negative x over e negative x is this. So it's e and x over e and x plus 1. And it's like this, I think, right? Because that's squared on the bottom. Yeah. Okay. I think that's right. Fuck it. Okay, so down here, this pow now can just be a 2 like this. Okay, and then can we call, like, print the backprop? And I guess for each of these things, can we print the gradient as well? Yeah. Okay. Okay, yeah, so the fact that we see zeros all the way down seems pretty wrong. Gradient 0 everywhere seems incorrect. So we must be doing something wrong. I would like to work our way down, like, let's just do like a more simple problem. Right? So can we say X is a tracked F32. Okay? And P is the result of like a multiplication of two numbers. Okay, so like 3 and 4. Okay, simple, right? We backprop here and we print this thing. Okay, let's start here. So we have 12 comes from 3 and 4. So what we're expecting to see here is that any change in 3 is like has the derivative of 4, right? We want him to be like any change in this results in 4 times that output here, and any change in this results in 3 times the output up here. That's what I would expect to see if I understand all this correctly, which very well I might not. And so the question is, why the fuck isn't that happening, right? So we come down here to mul. Hello, what is fucking that there was like some like stuff hanging around there from bad rendering. So oh, we're not recursing. Yeah, that's why. So we need to do in one backprop and into backprop. So we need to do that here, here. This one only has in one. This one has in one and in two, and this one's in one. Still no, huh? Backprop. Let's start here. And can we say what operation this is? Backprop mul, backprop init. So we're actually getting here, right? We should be here, and we like, why is this not doing anything then? Oh, val here, not gradient. Oops. Oopies. Whoopies. Nice. Okay, so this makes sense to me, right? Any change to the number 3 will result in a 4 change in 12, and any result of 4 will result in 3 change in 12. That, I think, makes sense. I think. And we can confirm that this is right by changing that value on its own and seeing that the net amount it changed is the same as what the gradient says. Right? So here, if we change 4 to 5, we should see this go up by 3, and this should become 15, right? Which is obviously true, but we can confirm that, right? And as we get into more complicated cases, we can like get a little farther down, right? So let's say, like, let's go back to our more complicated thing. Right? So we run our network on these two numbers. We say, hey, how does this thing change the answer? I need to print the network. Oops. From loss. Okay, so here we go. Like if we change the value, hold on. If we change, it's so hard to track what each of these things are. Should we add names to them? We could add names to them to make the things a little easier. Or we could actually just do this. Let me print the gradients for network weights 0. Right? So we think that if we change weight 0 by 1, the output number should change by 3. Which seems impossible to me. That seems impossible, right? Because the output is a number between 0 and 1. Because we were supposed to multiply this by his parent gradient. Or downstream gradient. Right? So each of these things, we're like differentiating that thing on its own, but his gradient is added multiplied by my own gradient, which I don't know yet until Yeah, there's something weird here. Like, I can only differentiate, like, until I've looked at the whole graph. Oh, god damn it. It's like, as we walk, we have to do gradient accumulation or something. Yeah, there's something there. There's something there where, so like, I know that the derivative of 3x is 3, right? But I need to multiply that by the derivatives on the way up. And so, like, on my graph of stuff that happened, loss, oh my god, my fucking scroll wheel is broken. Loss, sigmoid, whatever. As I like go down this chain while I'm printing, do I multiply gradients together? But even that doesn't really make sense, because here, when we're adding to the gradient, he needs to be multiplied, like, he needs to be multiplied by how much he contributes. So it's almost like, before we go down a layer, we need to know. Hold on. Hold on. So the idea here, like, if we have A is used in like two things, his contribution to this, or to like the final answer, I guess, like both of these are used in something here. His contribution is only known once we know his contribution, which is only known after, if this network kind of went like this, right, where he's used in like two things that are used in the final answer. Like, we only know his contribution once we know both of these guys' contributions, right? So we can't kind of do depth first search, you know what I mean? You have to do breadth first, so that you make sure that, like, but even then, like, I don't know if these things come in like nice clean layers like this necessarily, right? Because, like, what if he's like this? Like, then what? you know? Uh, so that's kind of interesting. Okay. So what if we change the rules? What if we calculate the what if we don't like accumulate him? Well, we have to somehow. Cuz like, the answer that we want to know at the very end, the answer that we want to know at the end is, how much does this affect the final answer? Which is the sum of how much he affects this and how much he affects this. And so the add thing does make sense there. It does. Um but it's that we have to know that, like, it's complete. Hmm. Okay, so I think it's easy to know. It's easy to follow this chain back, and it's easy to know that when I get here, I can say, how much does this affect this answer through this chain? That's like a very like easy to do operation. Which means that we have everything we need if we walk the whole graph. So it's that, like, Backprop needs like to take in like parent amount or something. You know what I mean? Like, or like downstream gradient. How much does this affect? How much is this affected everywhere else? And here we just multiply everything by downstream gradient. Every time we modify these guys, I think that makes sense. Yeah. And then as we continue down, yeah. So in one grad is this. Okay, this seems like it goes somewhere. This seems like it goes somewhere, right? And then we pass in one grad here, and then it kind of just like makes it all the way down. Are you just building And in Infer, you do have a training target in mind. The barcode scanner. We're eventually going to get to the barcode scanner. The optimization benefits of single layer training are hard to overlook. I agree. I agree. I just want, like, eventually this is going to turn into like GPU training, probably. But I just want to get like the basic idea down first. You know what I mean? So that like I have a better handle on it. I feel like doing like the stupid slow thing first and then optimizing later will result in like a better answer. You know what I mean? You know what I mean? Because like stuff like this, I wouldn't like understand yet. That like this is like a like this is a discovery that I'm making right now. Are you actually? Are you guys only showing? It's like a funny chain of events. It's like not actually because it's like the right answer. I understand that. Okay. In 2 grad is this. And in 2 grad. And then in 1 grad, in 2 grad. I think that this makes sense. I think, but we will see. Kyle wants to track calories for the app you need barcodes gonna need neural network. Yep. Exactly. Simple. Okay. Boom. Okay. In 1 grad here is this stuff, which goes in here and here. This is in 2 grad equals this stuff. Yep. And please God, tell me we're almost there. Almost. Okay. Boom. Okay. And then here, this is 1.0 for the initial multiplier. Okay, this looks... Oh, wait, hold on. What is happening here? Okay, yeah, so this is saying that changing the weight by 1 will have an increase in the final answer by 0.75. So here is the, like, loss. Yeah, okay. So we're saying if we change weight 1 by 1, this will end up at the answer of 1. I think that's what it's saying, which we can find out, right? We just put a 1 in here. And no. That is not what happened, which makes sense because that would be like quite extreme. Oh no, sorry. Oh no, yeah, 0.75. And then this one also is like 2.5 is wrong. So we've still done something wrong here. I really thought this like going down would make sense. It felt right to me. It felt right, but now I'm not 100% sure. Can we go back to like a simpler case? Can we go back to a simpler case? Okay, so in this simple multiply, a change in 3 by some amount will go up by 5. Okay, let's try to do something like, can we divide this entire answer by 0.5? You know what I mean? Or sorry, divide by 2, multiply by 0.5. So my understanding, if we do this, is that the amount of change for each of these guys is going to be halved. Right? So here, you know, the total answer of changing 3 by 1 should be that this goes up by 2.5, right? So change this to a 4 and we should get to 10. Okay, so that's good. This seems to work the way I would expect. Now, can we try adding in like some other operations, right? It's very likely that some other operation is fucking us here. So can we now do, I don't know, try track def32 pow. So let's take the power of this to 2. Okay. Cool. Okay, so here we're saying that like a change in 4 by 1 will increase this by 50. So change this to 5. We should see 150 here. Okay, that's not quite right. So that's interesting. That's interesting. So, oh, but of course. Of course. Okay, I'm a dumbass. Wait, this might just be working correctly. Of course, of course. So, if I am on some like parabola, and right here we say, hey, a change going over by 1 will result in us going here. Like, that's not true, right? Because in real life, like that's the derivative is only correct for an infinitesimally small movement, right? And so if we have like a real parabola, the real change is like more than that, right? So I think this might just be right, right? Because we overshot by our estimate by a little bit, as expected. Oh, Christoph, thank you for the raid. Sorry I missed that. Appreciate it. For those of you who came in, I apologize. You've probably been watching for 5 minutes being like, he's just talking, but we're trying to train a neural network from scratch. And we are just starting to get through like backpropagation, right? So we have a series of operations that happen. We kind of like build a node graph of all of those operations, and then we say how much did this piece of that node graph contribute to the final answer? And we're doing that with like, we have derivatives for each of the operations that we support right now. This is not how this will end up, but this is how it works for now. And yeah. We are then going to try to train something with that, but we're not there yet. Okay, so I think this might be working. Maybe. I mean, it's not like we could write some tests, but what if we just fucking winged it? Wing-dinged it, Yeah, fuck it. Let's see if we can get this to do the thing that we wanted it to do, right? So we say, hey, we have two numbers. We want to know which one is bigger. We have gradients now, like theoretically, assuming that we did everything right. And so let's do a training loop. So our training loop is probably, oopsies, wrong thing. Okay, can we, first of all, say we have like a loop arena? Right, a lot of the calculations that we're doing here are going to live in one batch of allocations. All of this stuff per training loop. And we're going to say, we're going to keep looking at like one number. We're going to keep doing this maybe once. Maybe we do like 10 iterations at once or something. Both of those are very reasonable answers. And then we will try to like nudge the weights and biases a little bit so that they look a little bit more right. I think that's reasonable. Because we have like a direction to move now, right? So we say like, while true, we pick two numbers, any two numbers. So we need something like RNG. Stood random default PRNG initialized to 0. I don't give a fuck. We pull up the random interface here, and on each iteration of the loop, we say, let's run this guy with A and B, right? So this is gonna be a rand float. B is a random float, and we're gonna throw A and B in there, right? I do want to scope these a little bit because I'm worried about getting like really, really, really big numbers and then getting nans. But I guess we can just say like, if we can kind of like run this whole thing and then check for nan at the end, I guess. Right? So we can say, if loss val, like, what is it, like stood math is nan or something? Yeah. Probably or infinity or something like that. Whatever. Um, this will work for now. Okay. So let's start here. Let's just run in a loop and okay. Everything in here gets loop arena now. Boom, 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 and then at the end of the loop we do reset. Retain capacity, I think, is fine. Okay, so here we're seeing numbers here come in. Nice. So we have our numbers coming in, and we're seeing that the gradients are changing a little bit. Now what I want to do is like just do a stupid thing. The real world of neural network training uses these things called optimizers, where they kind of like use some heuristics to figure out how to move each of these weights according to the gradients, right? Right now we have the information of like how much does an infinitesimally small change in this thing affect the final answer. And I suspect that if we do the stupid thing of just nudging everything in lockstep, we're not going to like really get a great answer. You can kind of imagine that maybe you want some like momentum to these things, right? So if they keep going over and over and over again, we're like, we need to keep going that way. You might want to speed up so that you get there faster. You might want to maybe only do some parameters at a time because like maybe changing 2 in lockstep is different than changing this guy without that guy, right? Like because of the fact that our gradients, you know, for parameter A depends on parameter B, right? Like maybe you wouldn't want to move them all at once every time. Maybe you want to do some subset. There are all sorts of like heuristics you could probably use, and I know that there are optimizers that people favor. But for now, let's just say we'll step every fucking weight in a direction by some amount, right? So we can say like net dot optimize. Yeah, we net optimize. And here, I guess, for now, we will look at like for self weights. Wait. I think we might have to put an ampersand here. Can we just say like we have some like learning rate, right? So like really small number, bump it like a little bit in the right direction, and we say like self or like W is equal to W gradient times learning rate. Plus equals. Yeah, so we just like nudge in that direction. We do the same for the biases. Sure, fuck it. Whoa, what's he pissed about? W val biases, biases. True, so true right now. But he's mad about like a double pointer here, which I'm confused about. Oh, because this is already a pointer. My bad. Right, of course. It's already a pointer. It's an array of pointers. Okay, so what I want to know is, are these numbers getting more reasonable over time? So if we run this thing, if we just look at like this like top number here, we can see that this value is getting closer and closer to 1. Eventually it becomes 1 actually, which is interesting. So maybe it'd be interesting to look at the weights here. That like indicates that we're getting very close to, oh. Hold on. We want the value to go to 0, no? We want the value to go to 0? So does that mean we're supposed to minus equals this shit? Yeah, here we go. We got this thing close to 0. Hype. Okay, so can we print the 2 weights? We're doing gradient ascent. I think we want minus equals. Yeah, I agree. Dude, it's so sick. Not that, like, I'm surprised that somebody can watch me just talking out loud, just bumbling around like a fucking idiot, and like understand enough to like correct the problem before I notice it. Like, that's so sick. That's so cool. Like, I don't know, like, what part of that is cool. It's just, like, surprising to me. Because I would think that if I just, like, bumble around like a fucking idiot, I'd be so lost in the sauce that, like, you can't tell. But it's kind of sick that, like, that indicates that there's at least enough human communication going on that, like, there's something of value here. And that's cool. I just think that's exciting. Anyways, that's sick. Okay. Value close to 0. And so what I want to do now is, I guess, look at the weights and biases. That would be kind of interesting to me. So can we look at, like, what did this thing learn? Because what I would have expected, from going way back to the start of this thing, I would expect that, you know, you have A coming in, you have B coming in, right? They're both coming in here. What can we, like, multiply, add to get this to go to 1 if A is bigger and 0 if B is greater? I think my assumption here is that you have weight 1 is, like, approximately equal to weight 2, but negative, right? And then that way, when this is greater than 0, A is bigger, and when it's less than 0, B is greater. That would be, like, kind of my assumption here, of what it would learn, but we don't actually know, right? But let's kind of see if that, like, our guess is good. So can we print maybe just the whole network here as well? Net. Okay, so give a second, hit Control C. Our loss is quite low. However, I guess that we don't really know if it's only low for this particular result. But, you know, we can probably hope. And so let's see, what do we get here? We get our weights here. Weight 1 is negative 2.1. Weight 2 is also negative 2.1. That's interesting. The biases here. Wait, is that true? This is one thing. This is the other thing. Biases is negative 4 and negative 4. So these guys are actually getting the same. They're actually coming into the exact same thing. Why are you assuming 0? Yeah, that's a really good point, huh? That's a really good point. If A is greater than B, expect... Yeah. That's a really good point. I'm surprised that it's converging on anything, actually, now that you think about this. So if A is greater than B, we should be like, I guess just like this. So if A is greater than B, 1. Else 0. And then I guess, like, if A equals B, like, let's just, it's fine. It's fine. Good eye. Good eye. Obviously, that was fucking stupid. Now, the question is do we still converge at all? Okay, so we are seeing, like, big 1 sometimes, big 0 others. Can we stop printing so much? Let's just print the loss. Let's just print the loss and see if it looks like it's converging. It looks like it has converged on sometimes being really fucking wrong and sometimes being really fucking right. I agree that visualizing is important, but I don't want to do that yet. Not yet. So, that's interesting. I would have thought that this can converge. I would have thought that this can converge. So can we start? Let's just start by pre-jacking this shit with weights that we think are correct. Does that kind of change the behavior? No, surprisingly. Surprisingly, it is still kind of getting to the point where it flip-flops. Interesting. Interesting. Okay, what is this thing doing as it goes? Let's... It could be that our learning rate's too high as well. That's possible. But our weights look like they are... Oh, wait. This is good. One positive, one negative. Okay, let's try this. Let's try doing a bunch of these at once, right? Maybe that will give it more information, right? If we're only letting it learn after one iteration, it's going, like, it might be kind of drawing incorrect conclusions. If we sum the loss with every iteration, I would hope that that does something more interesting. So can we go like var loss is equal to attract floating point 32 with that's initialized to 0. Then for like 0 to 1,000. Okay, we add to that loss. Right? So we go like loss is equal to loss, add the current loss and loss. Okay. Then at the end of that we do backpropagation. And then we try to do something. That might be interesting. Who knows if that'll work, but maybe. Oopsies, this should be try tracked floating point 32, add this loss and loss. Okay. So printing the whole network is like a disaster now because it's like getting super fucking nested. It looks like we are getting to nan on weights at some point, so maybe we like reduce the learning rate by even more. Or maybe here we normalize the loss. You know, to like be within 0, like the same order as when we were doing one at a time, right? Because right now, like as we add, the number's getting bigger and bigger and bigger, but we can say like, okay, we did 1,000 of these, so divide this by 1,000. Maybe. I don't fucking know, man. Don't ask me. I'm not your mom. I don't know why. Okay. Let's try that. Try track 32 mul. Init. Yeah. And I fully understand that this interface blows fat nuts, but whatever. That's interesting. Why did it stop? Oh, because things are getting to nan, which is really bad. So, I guess my gut here says that reducing learning rate will prevent us from getting there more, but maybe not. Maybe it's like diverging it by mistake. Because it does seem like the loss is growing here. You can see this number like steadily increasing, which seems bad. No? Like, to me, that seems bad. Yeah, that's kind of funny. So, like, kind of unconditionally, this shit is growing. What does Backprop 1.0 mean? It means, like, the 1.0 is how much of, like, proportion of the total this thing is. So, as we, like, recurse into this thing, we basically, this number reduces towards 0. Because, does it? It multiplies with the other gradients that it's going towards. Yeah, I think so. Not reduces towards 0, but like it's like how much do I affect the final answer? Well, if I like multiply this thing by 5, then like it's gonna have 5 times the effect on the final answer. So that should be captured as we go back down the chain. You know what I mean? So we start with 1.0 to be like multiplier 1.0. I do not like the fact that this is growing. Like, just consistently growing. And it is funny that, like, if we watch these numbers, I guess, like, what's happening is they're trying to get more and more extreme. Learning rate is already quite low. I agree, but, like, the fact that it was getting to Nan seemed bad. It could be that, like, we're, like, hitting local minima, though. But yeah, we're getting into Nans so quickly, right? So that's why I, like, reduced it a lot, was to try to avoid that problem. Okay. So how do we debug this? How do we debug this? I guess we should look at the gradients. Okay. So what are we seeing here? We should be seeing that, like, the gradient. Okay, can we log the inputs here as well? Let's log the inputs here. So let's do std debug. Yeah. Okay. Print inputs A, B. Okay. Output. And can we print the gradients for weight 1 and weight 2? I think that's what we want to look at. Oh, fuck! Our gradients are accumulating. Our gradients are accumulating. Fuck. For self, W gradient is equal 0. B gradient equals 0. They're accumulating over time. They're accumulating over time, which is not helping us. Okay. Wait. Does that fix the problem? Okay, learning rate maybe is too low now because our gradients are fucking way smaller now than they used to be. We could go higher here. Okay, so what do we see happening here? If I, like, stare at these numbers, we kind of see them just kicking around in the same area. They're kind of growing in magnitude, but they are both negative, which I don't really like. I don't like that. Can we... Can we increase the learning rate even more? Okay, so if I increase the learning rate up to here, we're actually seeing, like, super stable numbers that are, like, consistently wrong, which is interesting. Also, I want to log the network before we clear gradients, I think. Okay. So we can see that, like, these gradients are resulting in very small changes to the final output, which is interesting. So, like, incredibly small. Incredibly small, which is surprising. Right? Let's get rid of this, like, multiply thing that we were doing to make the gradient smaller. But, I mean, these still are, like, incredibly tiny numbers. Incredibly tiny numbers. So, the question is why? I would think that as we go through these, the gradients would accumulate for each thing we add. If I, like, so we're seeing, like, order of magnitude E negative 22. If I, like, increase this number of iterations per thing a lot, oh, we're getting nans, like, immediately. I guess that makes sense. Okay. How... I guess you could, like, break out early if the loss is too big. You know? Just to, like, prevent it from, like, getting kind of fucking crazy. That's, like, seems kind of reasonable to me, because otherwise the gradients get too big, probably. Can we drop this to, like, 100? Okay. So now our gradients are more reasonable. I mean, we are seeing these values still being very stable. And again, like, can you double check the exponential derivative? Yeah, it's probably worth doing, huh? Probably worth doing. So here we have derivative of sigmoid, which is this. We have e to the negative x here over e to the negative x plus 1 squared. So I think that's right. I think that's right. Okay, well, let's look at the loss. I think we just have to look at the loss for each iteration, right? We have to. Right? So what are we expecting here? Cuz like if this is wrong, then we could be in trouble. Ignoring inputs and outputting the same answer no matter what would give you 50%. I agree. Are you dividing? I think so. Right? E and x over e and x plus 1 over e and x plus 1. That's over squared. Seems reasonable to me. Seems reasonable to me. Okay. Let's double check that our loss is right. So in, out, loss is this loss. Yeah, okay. He's mad because this needs to be dot val. Okay, so here we get this is supposed to be greater than this, right? So he's giving me 0, which is loss 1. This greater than this, he's giving me 0, which is loss 0. So it does seem to me like the losses here are correct. Okay. Now, when loss is 1, can we print the gradients here? So let's go back to optimizing every iteration of the loop. So yeah, let's do this. Let's get rid of this guy, this big loop here. I suspected that might help, but maybe he's getting confused. So let's do this. And can we print the gradients that are associated with each weight? Ooh, and then I guess here we also have to do like a clear grad or something. We're kind of missing that if we're okay, for self weights w gradient equals 0 and biases, boom. It's fine. And then here we do self clear grad. Maybe this should be kind of an external thing, but whatever. Okay. Can I not print the whole network? I just want to print gradients. So can we say like, maybe we do print the whole network. Fuck it. Okay, that's fine. So give him some time to think. And, ooh, wait. Oh no, here it's still big. Okay, so in the case where loss is high, what is happening here? We have No, we need to log this better. It hurts my brain too much. Stood debug print. Weight 1 is this. With gradient 1 is this. And then 2 like this, and this is net weights 0 val net weights 0 gradient. Okay. Okay, and then I'm also gonna I'm gonna ignore biases here because I don't believe that we should need them for this problem. And so not applying those gradients might help me just with like understanding. You know? Okay, so when our loss is really big, changing, like these guys have like the same direction of gradient, which surprises me, right? I would think that they should move in opposite directions. Can you try expected -1 instead of 0? Am I a fucking idiot? Am I a fucking idiot? No, sigmoid does end up in 0 to 1. I guess we should double check that we're calculating sigmoid correctly. But I'm pretty sure 1 over 1 plus exponential of negative input. Yeah, that seems right. That seems right. So I think that this is true. Our loss we feel like is correct, right? It should be like approximately, 1 when this is wrong. So if this guy is supposed to say A is greater than B, so his output 0, his loss is big. Now, it's the gradients that I'm more concerned about here. It's the gradients that I'm more concerned about. Can we maybe print net loss again? Let's see how these gradients are like propagating. Right? So loss big here. So any change to this guy results, a 1 change here results in a 1 change here. That makes sense because it's an add. Then subtraction of this guy. If we got sub reversed, that might be a problem. Is our gradient on sub wrong? No, I don't think so. So any change to the second parameter is negated. Okay, so that seems right. Okay, so give him a sec to think. So here we say this is a big loss. So what are we expected to do here? My weights at this point are... Actually, we should look at the... I need a marker here. I don't know where it starts and where it ends. Stood debug print new loop. New loop, baby. Okay. So here we have weights. They're approximately equal. The fact that they're approximately equal is kind of interesting. I guess maybe that's just kind of like luck of the draw. But there is something there. Our loss here is high because A is supposed to be greater than B, and we return 0. Okay, so we should be seeing that weight 1 here is -4. So that's this, right? Yes. And so let's walk it back. So this thing has like full contribution to this addition. That makes sense. Like 1 change in here makes 1 change in here. Then here we're saying I have a sub. Like how is one change here resulting in -1 change here? I feel like the fact that this is negative is like flipping something here. Oh no, I guess that's right? So if we have a parabola here, right? and we're at x is -1 here. Like, moving 1 forwards results in some downwards movement, so I guess that is right. Okay, and they're saying that the contribution to this is like approximately 2 times the movement, right? Which makes sense because this is a power thing, so this should be doubled contribution. Okay, cool. Sigmoid. Check out your hard-coded weight 1, -1. Yeah, I agree with that. It does make sense. If I believe the answer should be +1, -1, then like, why the fuck would it be any different? I agree. Yeah, so we don't optimize, look at the gradients and see what happens. I like that. So no optimize. And hard code 1, -1. Okay. Or maybe even like 1000, -1000 is honestly more what I expect this to end up at. Ooh, interesting. So we nan here, which is interesting. Yeah, that's bad. Okay. We'll go back to 1 and -1 then. Or maybe like 5 and -5. And then maybe we shouldn't be using any arbitrary float for our inputs, to be honest. Like, float. Oh, this is, wait, this is evenly distributed in the range 0 to 1. Wait, then what's the problem? Okay, so yeah, why can't I crank these numbers then? That feels like it should be fine. But sure. Okay, so it does look like here like we have loss of 0.13, but the losses are relatively low. It's just when the two numbers get close together, the loss increases, which makes sense, right? That does make sense. Oh, so I guess if we roll poorly at the beginning, it could be that, like, they just learn that they have to get more extreme, but it starts getting more extreme in, like, the wrong direction initially. Based off of, like, the first few rolls. I guess that's possible. That is possible. If the hardcode version is correct, shouldn't the loss be 0? Well, no, because what I'm imagining as the correct answer is that, like, because, like, you have some smooth function, as, like, the two numbers get close together, they're just gonna be, like, closer to 0. You know what I mean? Or, like, less sure, I guess. Based off of my, like, understanding of the problem. Which is fine. Okay. So, okay, let's go back. Okay, what I actually want to do is set both weights to 1. And what I want to see is that they should move in opposite directions. I want to see, like, when it's wrong, he wants them to go opposite ways. Which we don't see, right? We see that the gradient here is positive for both. It's just, like, less positive. And that's what I don't like, right? I want them to move in the other direction. So I guess the question is why? Why is that the case? Okay, let's think about this. So we have 2 inputs. We're expecting them to go to 0, 1. And we want to say, how do we make this squared error smaller, right? So in this case, we have, like, 0 minus 1, square that shit. So we have, like, -1 squared, it becomes positive again. So the loss is always positive. So I guess maybe he's, like, somehow losing the information of like theoretically, he could be losing the information of no, because he should still know that like decreasing his value will make that number go down, I think. I think. Okay, so we see here what? This is saying that like our sigmoid returned 0.74, right? And we wanted him to return 0. No, we wanted him to return 1 here. A is greater than B. Okay, this is not a helpful one. I want to look at something where like the loss, where he got it wrong. Okay, like here. So here he wants to be returning something that's close to 0. Should sigmoid's backprop multiply by upstream backprop? I think so. Which he does. He should. Does he not? Did I fuck that up? I don't think I did. Oh. Yes. Yes. Good call. Good call. I like it when you guys solve my bugs for me. And while we're here, let's make sure that we didn't fuck that up anywhere else. Downstream, 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 downstream. That's a good fucking read, dude. Oh, and then I guess for now we can try turning optimization back on and see if the like it does what we expect now. Wait, good fucking read, dude. Good read. That's sick. I think that this might be doing the right thing now. Look, the weights are fucking positive and negative from each other. Let's fucking go! Thank you so much. That would have taken me a long time to find. That would have taken me a really long time. But I think that you just found the right answer. I think you found the right answer. That we just weren't fucking backpropagating our sigmoid correctly. And that was causing problems. So, wait, hold on. Let's get rid of a bunch of this debug info, and can we just print the loss? I want to see loss go down, baby. Stood, debug, print, loss, this. Mod them. Yeah. Well, just because they gave a right answer doesn't mean that they should be able to have unrestricted authority on the channel. New loop? So what we're hoping to see is like the number of zeros like increase on average over time. And it does seem like it, at the very least, is mostly correct. That's fucking sick, dude. Let's go. So yeah, it looks like if we look at, can we print the weights as well? Nice. So this is doing what we hoped. That's so sick, right? So the weights are approximately equal and negative from each other. Hell yeah, dude. Can we bring the biases back in? Not that I think that it should matter, but I'm hoping that the biases, I would think that the correct answer for them, for them to stay around 0. Can we do biases here? Biases? Okay, so our biases are staying relatively close to 0, right? We see them kind of like sitting around, which is kind of interesting is they like stay equal to each other. But I guess maybe like we didn't really randomize them, their start conditions. So we could do here. Let's take in a random thing here and just do like like float. Can we multiply this? Like we want this to be in some range, right? So times 2 minus 1 should give us a -1 to 1, and then we can multiply that by like 1,000 or something, right? Let's just like, or maybe like 10, right? Let's get these in the range -10 to 10 or something. Boom, 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 boom. How do I fuck this up? Like this. Okay. Uh, network initialize. So this guy should take in our RAND interface. Okay. And interestingly, the biases do not seem to like even themselves out. But oh, does our loss eventually end up somewhere sane here? No, but maybe he needs more time. Or maybe we need to like increase the learning rate. Maybe we need like a bigger batch. So we do have to be careful here a little bit. But let's go back. I don't want to run too many experiments because it is exciting that we did at least get to a right answer one time. You know? That's kind of hype. So this is kind of where we ended up. I think we weren't using biases in our training. We left them at 0 and we initialized these to 1. And yeah, here we go. We can see that the weights are growing over time. If you watch this number, they kind of started at like, I think I saw them start like towards 0. Like we're seeing like 9, 10, 11, 12, 17, 22. Yeah, they're growing kind of in opposite order of each other, trying to stay similar. Fuck it. I think this is a good place to call it for today. We're at like 2 hours. We have the world's simplest neural network trained. There's a lot of things wrong, right? Changing parameters is causing us to be incorrect, but he is learning to determine which of these two big numbers is bigger, which means that the like framework for training here is like sound. It's not efficient, right? The way that we've like tracked all this data is wrong, but we have, I think, correctly gotten to like some like real back propagation, which is exciting, right? We have this floating point tracked thing, which like is like like inserts itself into some node graph. He says, "How did I get here?" From like the past operations. He like walks himself all the way back and calculates the gradient for some final answer, right? Where our final answer is how wrong were we? We then know that like how much does each parameter in our network contribute to that thing. We also calculate a bunch of extra shit that we don't need, which is bad. Really, we should probably only be calculating gradients for stuff that we care about, but that's a problem for another day. But we did get to the point where we could say, hey, let's walk this back, figure out how each parameter contributes to the final answer, and then let's just try to like nudge them so that that number gets smaller. And that seems to work, which is very exciting. Very exciting. And it only took a couple hours. Now, obviously, you know, we need to get into the, like, this needs to go on the GPU, we need to support doing batches, we need to support a bunch of stuff that, like, runs this on, like, more reasonable data, we need to find a good optimizing strategy, all sorts of stuff. But I'm just happy that like the very basic idea of backprop here is working, and that's cool. So I think we call it here for today. There's lots more work to do. We'll be back probably tomorrow. It depends on if I've done enough reading tonight to like make progress tomorrow. We'll see. But yeah, if you like what we saw, we stream most days. We aim for 12:30 to 4 o'clock Pacific time. It is 3 o'clock now because, you know, we don't have, like, some segment of the stream is typically, like, cleanup, reading, whatever. And because it's, like, new project, there's not a lot of that to do. So, stream's ending a little early. Some portions, like, some streams go on YouTube. Some portions of some streams do not. The metric for that is whether or not I think it's, like, titleable, thumbnailable, clickable, whatever. So if you want access to the VODs that don't go up to the YouTube, we post them on Patreon. They're on Twitch VODs, or if you like sub as a YouTube member, you can get access to the rest. We do that so that we have something to give the people who want to support the stream. The stream will stop happening when I run out of money, right? So this is a good way to be like, if you want this, you know, to signal that the stream should continue, you know, you supporting on those platforms does directly contribute to the lifetime of the stream as a whole. So please consider, but obviously no pressure. Yeah, I think that's all the plugging we got to do. Thanks for watching. YouTube, peace out, and Twitch, let's find someone to raid.